and I need to tape, and I apologize that I was not taping. Who was it? Somebody can't be here today. A couple people. I apologize. Jennah, Megan, Munia. I apologize, you guys. I didn't get you the beginning of my discussion, but that's okay. All right. Then we're plugging in our limits of integration. And then not quite our final step. Step number 3 is we're going to evaluate the limit. So, evaluate the integral. Evaluate the limit. Step 1 is to rewrite as a limit. And then step 3, evaluate that limit. As t goes to infinity, 1 divided by an infinitely huge number goes to 0. So my final limit is just 0 plus 1, right? So the limit as t goes to infinity, and let me write this out here, the limit as t goes to infinity of negative 1 over t plus 1, this goes to 0, and so my final answer is just 1. Step 4, and we haven't talked about this yet, but this is where you decide if your integral converges or diverges. If you get a finite answer, your integral is said to converge. And so we would say in step 4 that this integral converges to 1. That means the area underneath that curve converges to the value of 1. It is a finite value, and even though this curve is going forever and ever and ever, never touching the x-axis, the area underneath that curve becomes a finite value. So we say it converges to 1. It's a pretty neat theory if you think about it. I mean, it really does have a lot of applications. The what if you kept going forever and ever? What does that mean? How does that work mathematically? That brings us to the type 2 improper questions on type 1 in Grill. You see the steps. Number 1, we have to take this abstract concept and rewrite it as a finite limit, okay, as a limit that we can work with. Then we evaluate the integral. Then we evaluate the limit of the antiderivative, and then we write converging or diverging at the end. Easy peasy. You guys are going to love this part. I mean, this is easy compared to the wrapping stuff around, right? Type 2 integrals. Type 2 integrals occur. Am I going too fast or are we going okay pace? Everybody's okay, right? Okay. I'm pushing us just a little bit because I want us to have lots of practice today. Type 2 improper integrals do not happen if you notice. There is no, I know it's really small. Can you guys see in the back that? And I uploaded new notes, I also want to say. There's new notes put up this morning, okay, with a couple different problems. But notice your integral doesn't have an infinity on it. So type 2 integrals are kind of like what you call hidden integrals. They're secret integrals that are improper because at first glance, you don't even think it's improper. But what makes it improper, guys? Why is this improper? Because we've got from negative 1 to 1, what do we have happening? We have a vertical asymptote. Do you see that? So you want to look at this and say, rational function, are there any places which is going to make a problem? And 0 is absolutely a problem. So improper type 2 integrals happen when you have vertical asymptotes or discontinuities in your integral. So I'm just jotting down what I just said. which is, this is called a type 2 improper integral because 1 over x squared has an asymptote at x equals 0. And x equals 0 falls in between -1 and +1. Like I said, these are more secret and they're harder to recognize because they're hidden. You don't see the infinity blaring at you, right? You just see finite limits, so you might skip it, but be careful. All right, so here we go. So what are our steps? The steps are exactly the same steps as before. The very first step that you must make when you're evaluating a type 2 improper integral is you want to rewrite the integral as a limit. I know I'm just spouting information for you, but we're going to practice 4 examples that you guys can try and work them through, okay? So you want to take and rewrite your initial integral as a limit. Now, what does that mean? That means when you have a type 2 integral, that you want to break it up so you can find that piece that's causing us trouble. So that means you have to first of all break up this integral into 2 subintegrals in this case. Not always 2 subintegrals. Sometimes it's just 1 subintegral that you first start with. But in this case, 0, because it falls in between -1 and 1, becomes my break point. Are you with me? That's my problem, child. So I am going to have to deal with that issue right here. This is an issue that I have to deal with by rewriting it using a limit. So I'm going to say, for instance, let's take the limit as t goes to 0 this time of -1 to t of 1 over x squared dx. I would want to do my other one too, but it suffices to say that start with 1, there'll be a pattern for what happens on the other side when there's symmetry like this. So I'm just going to start with the first one. And I'm going to replace 0 because that is not allowed. That is not proper. I cannot do integration until I get rid of that and put something in that's finite. Are you all with me? Now, when we talk about this, we are heading to 0, but which side am I coming from? If I'm coming from -1 to 0, which side am I coming from? I'm coming from the left side. Are you with me? So what do we need to put here on this limit? We're heading to 0 from the negative side or the left side. So when you do improper integrals of type 2, right, you're heading from a certain side. Infinity, you're just heading to infinity. But when you're hitting to a number, you want to go from that side. Okay, awesome. Because sometimes, maybe not in the case of 1 over x squared, but 1 over x, they might be going different places, okay? So you have to be a one-sided limit here. Alrighty, here we go. That's step 1. Rewrite the integral as a limit. Step 2. You want to evaluate your integral now. You guys are such a good class. You're so quiet. I know this is so boring. It's like process. You guys are just so nice. You're just so kind. Okay, here we go. You're going to evaluate this down. We've already done it several times, so I'm simply going to skip a lot of the steps, and I'm going to go straight from 1 over x squared is x to the -2, antiderivative is -x to the -1, limit as t goes to 0 of this, and so now we're going to, once we evaluate the integral, and this becomes the limit as t goes to 0 from the negative side of -1 over t plus 1. Nope, that's not right. -1. Erase. Let me see. Hang tight. Oh, I'm skipping too many steps. So I've got a -1, but because it's the bottom limit, I've got another negative in front. Is that right? I should have a negative right here, guys. I should have a negative right here. Evaluate the limit. Okay, help me out here. As t heads to 0, meaning you get infinitely small numbers, what happens to the whole thing? It does what? What is that limit, guys? Limit as t goes to 0 from the negative side of 1 over t. What is that? We're heading to really small numbers, right? We're heading to really small numbers. So maybe you want to go like 1 over 1 over a millionth, right? Something like that. You can think of it that way. You're putting really small numbers down here. Are you with me? Where's it heading, Griffin? It's heading to infinity. Well, this guy is. Because I'm heading from the negative side, my bad, I'm actually heading to negative infinity. Okay? But I've actually got a negative in front of that negative infinity. So 1 over t, when you go to 0 from the negative side, heads to negative infinity. I have a negative in front of that negative, so it's really heading to positive infinity. Do you guys see that? Quinn?
Why is it in the red? Why is it negative infinity if both sides are going up?
Good. Excellent question. Excellent question. Okay, notice my final limit is infinity, right? Because I am taking a limit as t goes to 0 of 1 over t. And my picture is 1 over t squared.
So it's negative, really, really small number.
So if I looked at my actual, if I close that graph and actually look at 1 divided by x, notice, so if I actually look at what I'm taking a limit of, thank you for asking that question, where am I heading as I'm coming from the negative side? Where is this graph heading? It's heading to negative infinity. So this part, does that make sense? So this guy's heading to negative infinity. I got a negative infinity, makes it blow up to positive infinity, which creates my positive area that I'm wanting, right? This is a positive area. If my picture was upside down, then it would be a negative area. But it's definitely a positive area. So this guy here, the area, the integral, is a positive value, infinity. So step 4, what we do at this point is we say, because our answer is infinity, we say that this integral diverges. And that has a lot of power to it. Diverging integrals, diverging values mean they grow infinitely large, okay? And often you want to work with things that are finite, but sometimes you want to know this is going to blow up forever and ever and ever. It's going to be infinitely large. So we would say that this integral diverges. Whenever you come up with an infinity or negative infinity as your answer, that improper integral diverges. Improper integrals are super easy. Number 1, identify what the problem is. Do I have an infinity or negative infinity in my limit? Or do I have a vertical asymptote, a hidden place? Once you identify, you rewrite your integral as a limit. It is a necessary step. You evaluate your integral, plugging back in that letter that you're using to make it a finite construct here. And then you go on to evaluate your limit, and then step 4 is decide, is this converging or is this diverging? Terminology that we're going to see again when we go into series. Who has questions? How are you? You ready to try a couple?
So we don't have to do the other side?
Nope, because, thank you for asking. Once you have some kind of an infinite, if you ever have an integral that you start with that has 2 pieces to it, if one piece diverges, that's enough to conclude that the entire integral diverges. Does that make sense? Yes. Because we're actually looking at the whole thing, and so if part of it diverges, the whole thing is said to diverge. Questions? If you're in your notes, okay, if you're following along, you don't have to put this down. We went through this whole process, but I go step by step. But in your notes, it's very rigorous. It shows you if you have a type 1 integral, you have infinity, you use your limit, you replace things, and and then you talk about what it means to be convergent and what it means to be divergent. So this is all in your notes if you like fancy formalized information. We are going to do 2 practice examples. First of all with type 1, because type 1 is easier to see, and I can see how it's very small. So let me put them side by side instead of up and down. Let me put this second one here beside here so that you can see it. The second one is 1 to infinity of x cubed e to the 3x to the 4th dx. So I'm just going to blow those up so that you guys can see those 2 integrals that we're going to work on, okay? So I want you to go ahead and evaluate. Oh, it's a power 2. Well, that's okay. That's okay. It's good. We just did a power 2. Let's make it a power 3. You guys didn't do anything yet, right? Turn that sucker into a power 3. Ooh, we could do a half. Nah, we'll do a 3. Let's just put a power 3 down there. Change that into a power 3. I think I better change that in my notes as well. All right, I'm going to wander. You've got 2 type 1 improper integrals for your notes to try, and then we'll talk about them, okay? So everybody tell me, step 1, make sure you write your limit. Step 2, evaluate that limit, or evaluate that integral. Step 3, evaluate the limit. Step 4, tell me if it converges or diverges, okay? So step 1 is most important. Rewrite it as a limit. And this first one is 1 over 3x plus 2 to the 3rd power. I'll write it bigger so you guys can see. Negative infinity to 5 of 1 over 3x plus 2 to the 3rd power. Wandering. I'm gonna wander.
The first question or the worst question? I know. That's the first one I read.
God bless you.
Excuse me.
God bless you.
Thank you.
God bless you. You might need to go get tissues, huh?
Do you mind?
Nope, not at all. Sounds like you've got a nose thing going, for sure. Guys, there are 2 problems. I'm putting up work for 1 problem. This is what I'm looking for, guys. Just to give you a heads up of what we're looking for, okay? If I think I make it look simple, but when you try it, sometimes we're getting all discombobulated. Number 1, I am looking that you rewrite the limit. Number 2, I am looking for a method of integration that you can use. Now, if you're using U substitution, those limits have to disappear, okay? You have to leave bubbles there, or you have to convert your limits to top limit, bottom limit, but I do not want to see a T and 5 if you put a U here, because T and 5 don't apply to U, they apply to X. So you have to leave a little gap for those limits, okay? You do your antiderivative, you go back change it into x's, and now my limits return. Do you guys see that? Because now I've got x's again. Now I can plug in 5, and I can plug in t. Notice what else have I done the entire time? I have carried this limit all the way through my problem. If you don't want to put the limit on each step and you want to write your problems vertically and then just put ... like an arrow saying limit all the way down, I'm okay with that. Okay? But you need to remember that there's a limit on this thing the entire way down. Okay? So I'm looking for this, not just at the first step, but I'm looking for it where it's important. Then we get to the infinity stage. And now we take negative infinity, we substitute it in. Infinity squared becomes positive infinity. 1 over anything huge becomes 0. This sucker right now, when you evaluate that limit out, that will go to 0. And the answer will simply be the rest, which is this finite number. And that's going to be negative 1 over 6 times, and as you guys said, that's 1 over 17 squared, which is 343? 289. Oh, Tina. 289. And that's actually a really big number. What is that? That's 4, 5, 17, 30, 34. We say that because this is a finite number, this integral, improper integral converges. Okay, the integral converges to this number. But do you see kind of what I'm looking for? This is what I'm looking for. You need to change it into a limit required. Use a proper integration technique. If you're using U substitution, you better not be putting limits through unless you change those limits to be X limits, or U limits, to U limits. Once you go back to X's, then you can re-put, or like I said, you can put U limits on here, which would be 3 times 5 plus 2, 17 on top, 3t plus 2 on the bottom if you did your change. Then you come back, put everything in, take your final answer, and get an answer. How are you guys with that? How did the second one go? Second one go okay? I'm looking for the same thing on the second one. Right? Did you guys change it into a limit to start? This guy needs U substitution again. I'm going to change my limits this time. My top U becomes 3t to the 4th. My bottom U becomes 3 times 1 to the 4th, which is just 3. So I'm just going to actually change my limits this time to show you can also change your limits when you do a U substitution. You would change to 3 and 3t to the 4th, and you would have 1 over 12 e to the u du. But notice this is good because this limit and this limit match U limits. They are U limits. They have changed and converted. I obtained them by taking my original limits and putting them back in place of U. 1 got put down there and gave me 3. So those are okay to throw on there. I don't have to put the bubbles. Or whatever, leave blanks. Antiderivative of 1/12 is just 1/12 e to the u. We are taking a limit as t goes to infinity of 1/12 e to the u from 3 to 3t to the 4th. So that's the limit as t goes to infinity. Oh, I ran out of space. 1/12 e 3t to the 4th minus 1/12 e to the 3. As t goes to infinity, e to the infinity grows infinitely large. And so we would say that this integral actually diverges. So again, do you see what I'm looking for on your test next week? Okay? Number 1, I want you to take your original integral and rewrite it as a limit. Number 2, I'm making sure you're carrying that limit all the way down. Number 3, I'm looking to make sure that you've done the proper integration. And if you're changing limits, changing variables of integration, you better change limits or leave gaps and put them back in afterwards. And number 5, I'm looking right here for an evaluation. Can you go from this step to this step? And then can you take the limit as t goes to infinity and show me why the piece does what it does? Quinn.
Sorry, could you explain one more time why 1 to t becomes 3 to 3t?
Absolutely. Are you okay that u has to replace 3x to the 4th?
Yes.
So u is my definition now. So my old variable was an x variable because it paired with dx. To make it become a u variable, I simply have to convert it into u's. So I go here and I put it where there was an x.
So, okay.
So
you
t,
plug it in for x in the u.
yes.
Okay.
You use your definition, and now this becomes a u thing. If you think about it, that's exactly what you would do if you went back to the beginning and re-plugged in, because u simply gets replaced with this, and then the number goes into that thing there. So yes, you find your u, use that to convert and make your top and bottom limits. Make sense?
Yes.
Good, 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 good. Questions? So here are my 2 examples right here. So your job is to recognize that with type 2 improper integrals, there's an asymptote or a discontinuity problem that you have to discover and then replace with the letter t or b or a or whatever letter you choose. And I encourage you to physically put these in your notes, work them through the process so that you have this muscle memory going on for next week. Very last problem of the day, because it's tricky. Oh, I gotta erase the stuff that's on the board. Sorry, guys. Sorry, guys. Oh, yeah, you guys can't see this. Give me a second. Let me clean these boards off. Oh, you can kind of see it. You can kind of see it. Here you go. Thank you, Jennah. Does anybody need me to want to take a picture? I'll actually turn that one blank over there. Display one blank? Nope, wrong one. Hang on. There we go. Does anybody need to take a picture? Were you guys all okay with this? Ooh, interesting. Ooh, this one's interesting. I'm not telling you if it's type 1 or type 2. You have to figure out, well, okay, it's got a problem here, right? Do we have other problems we have to worry about? Are there problems in the denominator you might need to worry about? I shouldn't call this problem 3. I should just call this last example. Okay. What are you guys looking at? What do you see there's an infinity here? So you definitely have to have an infinity. What part would make this 0, 6, or 1/2? Those both fall outside my interval, so I'm okay. The only issue you have with this problem is your infinity. So there is one issue. You should have the limit as t goes to infinity on this problem. Let's say that again. So first of all, we have infinity. That's the issue number 1. Number 2, x equals 1/2, x equals 6 would be the problem, children, down there. That would give me 0. But neither is in your interval 7 to infinity. So you only need to worry about infinity. If it was x minus 8 underneath, then I'd have to also worry about the 8. Are you with me? Do you see what I'm saying? But in this particular example, those two values that make your bottom equal to 0 are outside your interval. The only thing that's creating our problem right now is infinity. So if I'm going to rewrite that as a limit, I would write the limit as t goes to infinity from 7 to t of 22 over 2x minus 1, x minus 6 dx. What is this? It's a rational expression. How do we solve this? Using what integration technique? What are you guys using to solve this with integration? Partial fractions? Ka-ching!